So, did anyone watch our first lecture on YouTube?
We watched it live.
Yes. Did it work for those? Did you watch on YouTube?
Yeah, you mean the first lecture we had function analysis?
Yes.
Yeah, just for the top of the board.
It's not appearing. I just wanted to know if. So the very top does not appear in the camera.
Yeah, not really.
Okay, so let's try to do something better today. How's everyone doing? Good? First class was okay? Okay, so let's continue then. So, this is the class 2, and today I guess I want to talk to you a little bit about approximations, let's say convolutions and approximations of the identity. And let's see. Let's start today by reviewing what we did last class. So, as I said, this is a course that is going to be of 20 lectures, where I want to give to you not only the basic and classic theorems of functional analysis, but I also want to branch out a little bit to topics in real analysis that I think you should know, some topics in harmonic analysis, Fourier analysis that I think you should know, since we won't have a class after this one. So this will be functional analysis plus some additional stuff for you. Of course, paying a price of perhaps not entering in too much detail in some of the topics, but I wanted to give you guys a nice overview of what I think are some of the main topics in analysis. So last class we discussed a very nice topic and very fundamental, right? So we discussed LP spaces, which is going to be a source of many of the examples that I will discuss with you in this class. So recall, say if we are, for example, on our N, on RD with the Lebesgue measure, Dx, so the class, say LP of RD was just the class of functions F, such that from RD to R, measurable, such that this norm that I baptized here is found. This is the LP norm. This is for 1 less than or equal than P less than infinity. And the case P equals infinity, the L infinity, are the functions, the measurable functions, such that the L infinity norm, which we define as the infimum of constant C, such that F is less than or equal than C almost everywhere, that this is finite. Okay. And we discussed some interesting and basic properties about these spaces. So we showed last class that LP is a complete normed vector space. Sometimes called a Banach space. So when you hear this word Banach space, don't get frightened, don't get upset. It's just somebody trying to tell you that it's a complete norm vector space. So that is a vector space. It's somehow clear that you can add up two functions and you fall in the space. You can multiply by a scalar in your field. Here I'm taking real valued functions, but you could take complex valued functions. That it's a norm, that this in fact is a norm, requires already some work to prove the triangle inequality. right? So we proved two nice inequalities that we proved last class was Holder's inequality. Integral of fg loses to integral of f to the p. Well, let's see. The 1 over p, and integral of g to the p prime 1 over p prime. Okay, so here, whenever you see these exponents p and p prime, these are conjugate exponents, so their inverses add up to 1. So from now on, or starting from last class, last Friday on, I want Holder's inequality to be in your toolbox, and you can invoke at any time. The case p equals 2 is just called Cauchy-Schwarz inequality. The other inequality that we proved was the triangle inequality, or Minkowski inequality. This is the triangle inequality, if you want. That stated that f plus g in a certain norm LP is less than or equal than the sum of the norms. This is what makes these spaces norm vector spaces. This is what makes this a norm. Of course, when you look at LP functions, I'm always talking modulo sets of measure 0. So two functions are equal if they agree almost everywhere. So we proved these two nice inequalities last class, and I also gave you a statement about the duality of these LP spaces, saying that this norm LP of a function f can be given as a supremum. So it's a supremum over all products of integral of f against g, where g is a function that belongs to LP prime, and the norm of g in LP prime is 1. Right? Let's say p here between 1 and infinity. You see that p equals infinity. This is a little bit of work to do. And I assigned to you as an exercise, so you could think at home, to actually prove that this is a complete space, that Cauchy sequences converge to an element in the space. Did you take a look at this? Is everyone comfortable with these facts on the board now? Okay, so this, believe it or not, this goes a long way. Now the topic, okay, so do we have any questions from last class that you wanted to talk about here? Maybe make a remark, something that you didn't understand? Or is everything fine so far? Smooth? Good, because this is what we're going to discuss today, smoothness and things. So the goal for today is to discuss some, maybe the goal for today and for next class, I wanted to discuss some approximation tools. Approximations by some, say, and here you can put whatever word you want, some smoother or better or easier objects. So I want to discuss today in the next class with you the concept of approximating a function by something easier, something smoother, something better, some function which is better or smoother or easier to handle. And this, of course, depends on the context. So what I want to discuss with you is the several possible ways that we have to approximate a function by other functions, especially when you consider approximations. And then, of course, here in this sentence, you have to take a close look to all the words that are here. You are going to approximate what? Say a function in a certain space. You're going to approximate how, in which sense? Pointwise, in the LP norm, or in the sup norm, whatever. So you can approximate in different senses your object by some other objects in a certain class. Okay, so I want to discuss a little bit with you about this concept of approximations today and in the next class. Today I want to discuss this concept of convolution and approximations of the identity, and maybe in the next class talk a little bit about the Stone-Weierstrass theorem. my plan for this week. Okay, so first I want to call your attention to this so-called dense subspaces of, say, LP certain domain. For the sake of discussion, let's be on Rn for. Let me just define what's the definition that I want. I want to talk about two particular important examples. One is the so-called simple functions. Let's be on RB for now. Okay. So whenever I talk to you about a simple function, this will be just a function which is a linear combination of a characteristic function of sets. Okay, so k here from 1 to a certain number n. Where, okay, so here ek is a measurable set. Whenever I use in this course, I will use this key of ek to denote the indicator function of the set. So sometimes you see with the Greek letter key, sometimes you see with the number 1 like this. So this is just a function which we call indicator function. It's just 1 if x belongs to your set, or if 0 if x doesn't belong to your set. So this holds for a general set E. So whenever you have a measurable set E, this indicator function of E is just this function. It's 1 if x belongs to the set, or it's 0 if x is out of the set. Okay? So a simple function is just a linear combination, a finite linear combination of characteristic functions of sets. Okay, so here AK's belong to the real numbers. We're talking about real valued functions, so you can take any sort of linear combination of this. So these are called simple functions. Of course, if you have just one characteristic function, it's a simple function. Another class that I want to call your attention to is this class of step functions. So whenever you see this word step function in the literature, it's usually the same thing, but with each set being a rectangle, or a cube, if you want. So it's the same definition. As above, with ek being rectangles okay. See if I want rectangles or cubes, or if it doesn't matter, rectangles is fine. So these are called step functions. So this means that rectangles, and when I mean rectangle, I mean a rectangle in RD, so it's with the sides parallel to the axis. So it's literally just a product of segments in the d dimensions, right? So this is a rectangle. So this is a subclass of this. Okay? This is a subclass of this. Good. Good. And again, a finite linear combination of things like this. You can either go further if you wanted to define over just cubes, actually, where the sides are all the same. You could define functions like linear combinations of characteristic functions of cubes. But what I want to remark is first that these classes of functions are dense in LP. So my proposition 1 of today is that these classes of functions here are dense in, say, LP of RD, then for 1 less than or equal to P less than infinity. Here, pay attention that I'm not including infinity. Okay? I'm not including infinity. When I talk about simple functions, EK is a measurable set, and this Lebesgue measure of EK, which I can denote with the bars or with the M, is finite. Okay? So it's a linear combination of characteristic functions of sets of finite measure. These are simple functions. Step functions is a linear combination of characteristic functions of rectangles, and rectangles, of course, have a finite measure. Okay, it's important that the sets have finite measure. So my claim to position 1 of today is that these classes of functions are dense in LP. Is everyone comfortable with the meaning of the word dense? Dense means that is, i.e., for any function f that belongs to LP, Rd, I can find a g in either this class or this class that is as close as I want when measured in the LP norm. Okay? We can find a g in this class, say, let's call this class, I don't know, simple functions. Let's call this class A, let's call this class B, A or B, such that f minus g, the norm of p is less than x. And for any f that's n, and given epsilon bigger than 0, we can find a g in either of these classes that it approximates your function. Have you seen such a statement before in your real analysis class?
Yes.
Okay, so let's just maybe recall the proof of this fact. So if you want to approximate by simple functions, let's say if you have a positive function here, say I have a positive function f that maybe will go out to very big at some point, infinity. So what you do is you just you fix an n, okay, you fix a big N, and you truncate here at the size n, and you also consider just the things from interval minus n plus n to minus n. So I'm just going to look at the function inside this big box. Let's assume that my function f is positive. I'll do the same procedure for the positive part and the negative part of f if I have two signs. So suppose this is the positive part of f. We just take a big box, n on the height, and a ball of radius n. So let's just take a look at the function inside of here. So the reason you want to take a big box is that you want these characteristic functions of these sets to have finite measure. And what you do here, for example, is you just split this height into a certain number of finite pieces. So let's just split this height in the number of, say, here you split in pieces of size. So if this is big N, each of these pieces has height 1 to the 2 over n. I don't know, something like this. Very small pieces. This height, right? So now you take whoever is in your graph of the function that lies above big N, you just say this is going to be the set 1, this thing here. Okay? Now, whoever lies between this and this guy, so perhaps in this picture, this set, this and this. This would be the set 2, this would be the set E1, this would be the set E2. Now, the set E3 will be whoever lies in between here and here. This, perhaps these guys. So you take, of course, these segments here. This is your set E3. Okay, so what you do is you construct a function f, let's say fn, associated to this big N, which is in the beginning, it's just a characteristic function of the big ball, Bn, okay, times a sum of functions if you want a sum of the functions g little k. K here goes from 1 to the number of pieces that you have here, which is a function of n times maybe n to the n times 2 to the n. And each of these gk's is one of the level sets here. Okay, so if the function is between this guy and the next level set, you just put it down, and that's the corresponding set. Okay, so this gives rise to a set of functions of this type, characteristic functions, like simple functions. And the nice property is that f is very close to fn at any point here, at any given point x. This inequality should hold. So f of x minus fn of x is less than, say, 1 over 2 to the n. Because for all x inside this big ball of radius 2 to the n. Okay, and now it's just a matter of iterating this process. So what you get is, if you increase your cube and you divide in thinner pieces, you get a monotone sequence going up. Okay, so you get a monotone sequence of functions, so it's going to be pointwise monotone, and it's going to go up to your f, and at each step is just a finite combination of some characteristic functions of sets. So by the monotone convergence theorem, these fn's are all dominated by your f, they're always below your f, so you can either use the monotone convergence or the dominated convergence, it doesn't matter, but this integral of fn minus f, the p will go to 0 as n goes to infinity. Let's say dominated convergence. Therefore, I mean, given epsilon, you can choose an n very big such that this gives you the idea. Is that roughly clear? Of course, one needs to write out the details for this, but it's the basic idea. It's just dividing your function in 10 pieces and always approximating by below. Of course, these sets here might be crazy sets. So this is why there's a difference between any sort of measurable set and rectangles. Now, if you really wanted to approximate your function by characteristic function of rectangles, then what would you have to do? So, and the idea here is to just perhaps
approximate measure sets by.
Say that again?
Approximate measurable sets by input.
Exactly, right? So if you know that you can already approximate your function by function of this type that have 100 sets, you just need to tell me how to approximate one set, and because this is a finite number, so if I can approximate one set as much as I want, then I can approximate certainly a finite number, 100. And then I just approximate one by epsilon over 100, and then approximate by 100 by numbers that are set. And how do you approximate one set E by cubes?
Because this is a finite measure, we have a collection of open sets containing it. How is that the difference? A measure is very small?
There's a property of the Lebesgue measure, right?
Yes.
There's a property of the Lebesgue measure. When you define the Lebesgue measure, you define, remember, the outer measure and so on. So, well, to talk about rectangle, I'm really talking in the RD. So if you're talking in a general measurable space, you just keep this definition of simple functions. But step functions hold for when you are in RD with the Lebesgue measure. This is a property of the Lebesgue measure that for any set, you can find a collection of cubes, actually. So you can find a collection of cubes, if you want. Disjoint cubes, such that it always covers your set. So meaning, given epsilon, there is a collection, that exists a collection, a finite collection of cubes, let's say union of cube j from 1 to big N, disjoint cubes, if you want, such that this is what we call symmetric difference, right? So this collection, let's call this collection C, is just a collection of cubes, such that C, sometimes they put with a little triangle. So the measure of C, little triangle E, which is just to say this is the measure of C minus E plus the measure of E minus C. This is less than epsilon. Let me write it. It's just the set of C minus E union E minus C sets. Okay? So you can approximate any set, any measurable set, by a disjoint union of cubes such that you cannot guarantee, okay, I will approximate from the inside. There may not be an inside. If your set, say, is just a lot of points here, and you want to say, I want to approximate by the outside. There also may not be an outside. So the right setting here is that you want to approximate. And the way to approximate is that you take the piece that is outside, that belongs to the collection of cubes C, and doesn't belong to E, and you take the pieces that belong to E but not belong to C, and this set has small measure.
I think you can do it from the outside and inside as well.
Yes. From the point of view from the outer measure, you can do this from the.
In the same picture you've drawn, you can.
You can do from the outside. Well, the outside part, the part that is, yeah.
But they couldn't be if they're from the outside. Maybe they're not finite.
Yes, I want actually a finite number. Yeah, exactly. If you want to approximate from the outside, maybe an infinite number. You could do.
Maybe the chunks away from each other.
Absolutely. If your set E had several different chunks away from each other, you cannot do with a finite number of collections. So this, if I want to do with a finite, there may be some small pieces of E that I don't cover, but I don't care as long as it's small. So and it's clear that the difference between the characteristic functions of this collection of cube and your set E, if this measure is small, the characteristic functions are very close. So this is why you can approximate one of these functions by a linear combination of rectangles. And then, so this is, if you're given an epsilon, first you approximate here, and this will give you 100 functions, and then you approximate each function by a collection of triangles with a factor of epsilon over 200, then you're okay. It is very important that you do this computation and these proofs at least once in your life. Okay? Do it, convince yourselves that these classes are dense, and put this on your toolbox. From now on, you can use this fast. Now, it is also important to make sure that this doesn't pay attention that this does not hold for p equals infinity. So these classes are not dense in L infinity, especially because the L infinity may have our functions that are just bounded, so they may have steps that go far away from each other. So let's see. That case p equals infinity, you have functions that are, say, like this. Function that from 0, you divide an integer 0, 1, 2, 3, 4, 5, 6, and here minus 1, minus 2. You can just put the function that's 1 here, 0 here, 1 here, 0 here, 1 here, 0 here. Any function. Or even the constant function equal to 1 if you want. I mean, you cannot approximate the constant function equal to 1 in the L infinity norm by a finite linear combination of characteristic sets with finite measure. Right? Because if your sets have finite measure, well, you have to think a little bit about this, but at some point, I mean, the measure of the sets where the function is 1 is infinite. So there will be a point, or at least a set of non-zero measure where the difference will be 1. so these sets like simple functions and step functions are not dense. Okay? Take f left like this, or simply f identically 1, and prove that this function cannot be approximated in the L infinity norm by functions of this sort. Okay? So whenever we talk about dense subclasses, we have to think about the infinity case a little bit differently. Are we good? Okay. So there is a lot of problems that we'll do in analysis where you will be asked sometimes, or you will need some point in your life to prove a certain property for a function in LP. And the way that you would go is to prove it for something simpler. So okay, if I need to prove this certain property for a function in LP, LP is a function very complicated. I will just prove for the characteristic function of a set. Then it might be simpler. I will just prove to a characteristic function of a cube. Might be even simpler. So once you know how to prove for this characteristic function of a cube, you say, well, maybe if I just take two characteristic functions of the cube, you can prove for linear combinations of these things, and it's going to be simpler. So then once you have proof for these step functions, you extend your result since the subclass is dense, to the whole LP. Okay? So let me give you one example so we can try to exercise this philosophy. So let's say proposition 2. So let me define, let me go find the definition. Let me define the translation operator. Okay, so let's see. If y is a point in Rd, let me fix a point y in Rd. Let us define the translation, which I'm going to call tau y of f, not x, I see, but f of x minus y. Okay, so I'm translating by y. So I fix a point y in Rd, and I'm going to define the translate of f by y as just this guy. It's a new function, okay? It's a new function that the value of this function at x is f of x minus y. And my claim, proposition, is that let 1 less than or equal to p less than infinity. Then this translation is a continuous operator on LP. In other words, then if y goes to 0, y is a point that goes to 0 in Rd, this norm of tyf minus f and LP go to 0. What I'm saying is that if you just take your function f and you translate, it's just like looking at your x's and just doing a little shift of y in the direction of y. So if you just look at these two functions, so if you do a very small shift, then you are still close. If you do a very small shift, then you're still closing the norm LP. So if y goes to 0, then this translation goes to 0. Okay? This translation goes to the same function f. So translation is a continuous operator in this sense. Why is this not true for infinity?
Because I can change one.
Because if you just take a function which is if you take a function like this, right? Just take a function like this, and you move it epsilon to the left, right? What happens with the new function? It's going to be like this, and here like this, right? But there will always be a piece such that the difference between the original function and the new function is 1. This piece is small but has no zero measure. So the L infinity norm of the difference is always 1. When y goes to 0, it's always 1, so it doesn't go to 0. Okay? So in L infinity, this is not true. But let's prove that, when p is less than infinity, this is true. Proof. And this is one example where you can prove for easy functions and use it, the denseness result. So, for example, if f is the characteristic function of a cube, so step 1, if f is just the characteristic function of a cube, you agree with me that this is true, correct? You agree with me that this is true because if you just take the characteristic function of a cube and then you just move y in this direction, so this is the new cube, the piece that it's not coinciding, right, is just this piece here. Let's call it, so this tau y of f minus f. The LP norm is just the LP norm of this characteristic function of this set, say EY. This is the set EY. Right? F itself is a characteristic function of a cube. When you translate by y, you have the characteristic function of another cube. Their difference is most of the time 0. It's just not 0 when you are at one and you are not on the other. This difference will be sometimes 1, sometimes minus 1, but since I only see the absolute value, it's just the LP norm of the characteristic function of this set.
Is the measure of A, dy?
Yes, which is just the Lebesgue measure of this y raised to 1 over p, if you want, right? And this goes to 0 because the Lebesgue measure of this guy obviously goes to 0. To 0 as y goes to 0. P is fixed. Right, so this set's measure essentially goes to 0. If you want, you can do the computation of this thing. So you know what to do for one cube. So if this is true for one cube, this is true for one cube multiplied by a certain coefficient. This is good for the characteristic function of the cube. This is good for 3 times the characteristic function of one cube. But if it's good for one cube, if it's good for 2 cubes, right? And I can take just and sum 2 of these guys. I do it in each part. Take epsilon over 2, take epsilon over 2, and do it. And it's good for any sort of linear, finite linear combination of cubes. Okay? So this is good for your, what we call our step functions. With cubes, or with rectangles, whatever you prefer. Okay? Now you do the general case. Okay, so what you do is you take any f in LP, okay, and what I do is take an f in LP of Rn, Rb, and I give you even epsilon bigger than 0. Give you an epsilon bigger than 0. I want to somehow prove that for y small enough, this is less than epsilon. So what I want is that I choose G, a step function, such that, let's say, f minus g in LP is less than, let's say, epsilon over 3. Okay? So I start with the general function. I'm going to choose a step function which is very close. And now, if you want to establish some sort of inequality for the translation y f minus f in LP, you do this nice use this nice idea of breaking this into 3 guys, right? So you want to put your G into play, because so you have to add and subtract G, right? So you start with F, you know how to solve your problem for a G which is in a dense class, and then you want to put this G into play. And you start with this object, so what you do is you tau yf minus tau yg, so you add and subtract this guy, tau yg, and then you add and subtract g, minus g plus g. So this is inequality. I have, in many situations in mathematics, the key idea is to do nothing in 2 different ways, right? So I'm doing nothing in 2 different ways. One is doing nothing, one is adding and subtracting the same thing. So the key idea sometimes is to do nothing in 2 different ways. So and then you have this nice expression, you break it, you use just the triangle inequality and break it into 3 parts. So one is, this is less than or equal than Tyf minus Tyg. This is less than Tyg minus G. And this is less than or equal than G minus F. Triangle inequality. Now, this first object here, if I translate f by y and g by y and integrate over the whole Rn, I haven't done anything, right? Because the Lebesgue measure is translation invariant. So this is equal to f minus g to the p. Okay? So you have here, now the distance from f to g is less than epsilon over 3. So this gives me this term and this term. This is less than or equal than epsilon over 3 plus something in the middle plus epsilon over 3. Now this term in the middle here is just the translation of g minus g in the norm p, which I know that it's going to be small if y is small. So this guy in the middle is going to be less than epsilon over 3 for y less than certain delta. And then I'm done. Because then I start backwards from y less than a certain delta. I know that this guy is less than epsilon over 3, then the whole thing is less than epsilon as I wanted. Are we good? Okay, so this is one example of a result that you're asked to prove a certain property for the space LP, but sometimes it's much simpler to think about dense subspaces. Okay, so sometimes it's going to be easier for you to prove the property for continuous functions, for C-infinity functions of compact support, for step functions, for simple functions. So some of these properties is just easier to prove for cubes. And then you extend by linearity. Take finite linear combinations and you're done. All right. So from now on, this is another result that we have in our pocket. Translation is continuous in LP, if P is not infinity. Good.
This makes LP separable, right?
This makes LP separable. As you will see later in this course, we'll discuss a little bit about separable spaces. Separable space is a space that has a dense and countable subset. So you can take, for example, the step functions with rational coefficients and cubes of rational sides with rational centers. Take this as your class. You can prove that it's still dense. This is your countable set of functions. This makes LP separable. P different than infinity. Infinity is not going to be separable. Think about it. All right. So other dense subspaces of LP, and again here I am still removing infinity, are the space of, which I'm going to call C of RD. these are the space of continuous functions. And I'm going to call C, I'm going to put a little, maybe I put the C here on top. So this is going to be, when I put a little compact here, this will be the continuous functions of compact support. Okay, so continuous functions are dense in LP, and continuous functions of compact support are dense in LP. As a matter of fact, C-infinity functions of compact support, these are C-infinity functions. C-infinity functions or C-infinity functions of compact support are dense in LP. Okay, so there's a lot of.
Are we going to prove it?
We are going to prove it, yes. Let's prove this. But I want to take a little bit of a detour and talk a little bit about the mechanism that makes us smooth out a function. This mechanism named convolution. Did you hear this word convolution before in your life? Everybody? Who never heard of this word before, raise your hand if you never heard of convolution before. Okay. So, this is a way to average a function. Okay, so this is a generalized notion of the usual averaging process that you have, and you may have. So, if I give you a sequence of numbers, and if I just tell you, hey, now you just change two neighbor guys by their average, it's going to be clear what you have to do. Or change each guy by the average between him and the two neighbors. It's clear what to do. So, a convolution process is just a way to average a function with the weights being given by another function. You don't see this very much from the definition, but I will, well, you have to know what I'm talking about to see from the definition, but it will be clear later on. So the idea here is simple. I'm going to give you two functions, f and g. Okay? And I am going to construct a third function named the convolution of f and g, which I'm going to denote by f star g, which at the point x, so these are functions in Rd taking real values. So f convolved with g at the point x is just the integral in Rd of f of x minus y, g of y, dy. Okay, so this is the definition. If I give you two functions, the convolution of them is a third function that at the point x is defined by this, the integral of. So note the subtlety of the definition here. So if I want to evaluate this function at the point x, so x here is fixed, so it's f of x minus y, g of y, dy. Note the symmetry here. If you just change variables, so if you just, x is fixed, if you just call x minus y equals t, this is just going to be the integral over Rd of f of t, g of x minus t, dt. Okay, so there's no preferred function here. Oh, why does the x go with f and not with g? No, f can go here or with g. Doesn't matter. It just matters that they're integrating over points that add up to x. The point x minus y and the point y, they add up to x. Okay. Okay, so this is the definition. and you see a little bit of what I was trying to tell you before. That by doing this at the point x, I am taking, say, pieces of f, say f of x minus y, and adding them up. So your x is fixed here, you're taking guys in the neighborhood of x, and you're weighting them by this weight g of y, and you're adding everything up. Right? So, but before I discuss this concept of approximations of the identity, let me tell you why this is nice. So, my next proposition to you is that the convolution is of two functions is always as smooth as the more regular function. So I'll put this in vague terms, but the convolution of two functions is as regular, let's put it this way, as the more regular of the functions.
As nice as the nicest also too?
Exactly. As nice as the nicest function. So if you want to write like this, it's even better. It's as nice, in terms of regularity, as the nicest function. At least in terms of differentiability, okay? In terms of differentiability.
Is it more?
Maybe more. Maybe that you get two functions which are not continuous, and the convolution is a continuous function. But what I'm trying to say is that, for example, if, for example, say if your function f is an integrable function, for example, and your g is a function which is ck of compact support, right? So if you have a function which is merely integrable, might not even be continuous, and you have a function which is ck, so k times differentiable with compact support, then this implies that f convolved with g is ck. So if this function has k derivatives, f convolved with g would have k derivatives. Okay? How do you prove such a fact? So the idea is to move the derivatives inside the integral where you have derivatives. So if you have derivatives in f, if you want to differentiate this in x, and if f is differentiable, then you would move the derivative here to x. Now, if my g is differentiable, then I will use this formula and move the derivative here to g. But suppose that you are on the real line, and then the case of Rn is the same. But so what you want to do is, so f convolved with g. Suppose you want to prove that this has one derivative in this case, right? So this is equal to the integral. Let's just work in one dimension because it's easy to visualize. So this is f of x, f of t, g of x minus t, dt. Okay, so if you're working in higher dimension, you do it for each of the derivatives in each of the directions, so it's the same proof. But suppose you are in one dimension and you want to prove that this function here has a derivative in, this function has a derivative at the point x. So you would have to look at that limit when epsilon goes to 0 of f convolved with g of x plus epsilon minus f convolved with g of x over epsilon. Right? You have to prove that this limit exists. It's the derivative. Then, when f convolved with g at the point x plus epsilon, you just use the definition. This is going to be integral of r of f of t of g of x plus epsilon minus t minus g of x minus t over epsilon. Okay? Now you want to invoke, remember, this, what I'm telling you, you have to get this philosophy throughout this course and throughout the rest of your life in analysis. So everything that you learn, make sure that you learn nicely and correctly, and you absorb the philosophy and put that in your pocket to be able to invoke. So everything that I'm telling you about what's an LP space, holders in the basic inequalities, the dense subspace, especially this, and also all sorts of convergence theorems from measure theory, this should already be in your heart. Okay, so I want to prove that when I move epsilon, so what do I want to show? When I set epsilon to 0, I want somehow to conclude that I move the derivative inside, so that f convolved with g prime is just, I move one derivative to the g, right? Which seems to be the case, right? So this, when epsilon goes to 0, this seems to converge to the derivative of g at the point x minus t. But when I set epsilon to 0, how do I argue this properly?
By Holder's inequality.
Holder here?
No. First, we need to change the over R to the compact support of G. And after that, we can conclude that G is bounded. If it's bounded, in this case, we can use the dominated or bounded convergence theorem.
Yes. So I have to somehow, to be able to move past the limit when epsilon goes to 0, I have to tell you precisely what sort of convergence theorem I'm going to invoke. So this, for example, by the fundamental theorem of calculus is, suppose that my G is Ck of compact support, let's say C1 of compact support. So this is bounded by G prime. Remember that this is G prime at a certain point, T star, right? The fundamental theorem of calculus, this is equal to G prime at a certain point between this guy and this guy. But since my function is C1 of compact support, its derivative is a continuous function of compact support, so it's bounded. So this thing here is bounded by a number, say 100. So this means that this whole integral, since f, I'm assuming here in a 1, so this is bounded by 100 times f, which is an integrable function. Okay? So this whole thing is bounded by an integrable function. Then I can use the dominated convergence theorem and move my epsilon to 0. Again, I'm going to tell you. This thing here is bounded by the G prime at a certain point. So it's bounded by the subnorm of the derivative. Since I'm assuming that my function is C1 of compact support, this subnorm of the derivative is the derivative is a continuous function, so it has an upper bound. So let's say 100. So this whole thing here inside the integral is bounded by 100 times f, which is an integrable function. So if you can dominate your object by an integrable function, you can move your limit inside. So arguing like this, when I move my epsilon to 0, this goes to the integral of r f of t g prime of x minus t dt. Okay? So this is how you move the derivative inside. So this is what I'm saying. If you have a function which is ck, you can move k derivatives inside. If you had that f was ck and g was ck, the convolution would be c2k. You can move k derivative to f, k derivatives to g if you want. Right?
But what if G wasn't of compact support?
What if G wasn't of compact support? You can still do it, but you have to pay a little bit more attention with this game of the convergence here. Okay? I'm putting this compact support just so you have the idea. Because I haven't actually told you when these things are defined. So I was very vague in the definition here, but in just general functions f and g, but it may as well be the case that this object is not defined, it's infinity or something. So you actually need to impose some decay conditions on f and some decay conditions on g, such that when you make this integral, you get a meaningful object, you get something that's not infinity. Okay, this is the topic which I'm going to tell you right now. But this philosophy that if you get two functions, you get the more regular of it, this is one of the principles behind the convolution operator. Okay, now, let me pose to you an inequality that's going to help you clarify this meaning, this thing, and when this particular convolution operator is defined or not. Okay, so let me maybe discuss two propositions. So, proposition 4. So, if f is a function that belongs to LP of Rd, and G is a function that belongs to LP prime of Rd, then remember, P and P prime are conjugate exponents. Then F convolved with G is, it's L1, yes,
It's a bigger one.
but it's actually a continuous function, right? So F belongs to L1 of Rd. No, sorry. This is no, it's not L1, guys. No, this is a continuous function. Continuous function that vanishes at infinity. This space is sometimes called C0 of Rd. So these are the space of continuous functions such that I given epsilon bigger than 0, there exists an n such that f of x is less than epsilon for x outside of the ball of radius n. Outside of a big ball, it's less than n. I'm not saying that the function has compact support. It's a function that goes to 0 at infinity. Okay, goes to 0 at infinity. The function, I mean, if I give you an epsilon, there will be a big ball such that outside of this big ball, the function will be trapped less than epsilon. The function cannot be doing what you see in the heartbeat example. Okay? I will prove this thing.
We use that.
Proof. Here, P could be infinity, okay? So here, let's just say, is that correct? Let's see, I think P could be infinity. So 1 less than or equal than P less than or equal than infinity. But let's see from the proof.
If it is not going to infinity?
No, I'm saying the P.
No, okay. Yes, but how to do the proof?
P, let's see. So here I have P and P prime. So assume for a moment that 1 is less than or equal than P, which is less than infinity. Assume that P is not infinity, okay? Because otherwise, so if by any chance P is infinity, you change the rows of F and G below. Okay, so if P is infinity, then P prime won't be infinity. And then you will be able to change this in the argument that I'm going to do. So if P is assume that P is not infinity. So what you have, let's see, what you want to evaluate. So we want to prove that it's a continuous function, right? So we want to prove that the translation by a certain number y of f plus g at the point x minus f convolved with g at the point x, this goes to 0 as y goes to 0.
Approximate G by
For any x, right? For any x. So this is what it means to be a continuous function, right? That f of x plus y minus f of x goes to 0 as y goes to 0.
Can we take step functions approximating one of them and doing this for f, for example, f with a step function, and try to take it, to use the density of this class?
You could do that. This would certainly lead to a proof, but I want to be more straightforward. I can maybe do directly with something that we already did by step function. So this is what you want to prove, right? So let me just write this thing. So it would be very easy for you to check, for example, that this ty of f plus g at the point x, okay, is just the integral of f of, remember, this is the original one, not x minus, let me change the variable, minus t of t dt, right? This is just the convolution. So if I want to translate by y, it's like changing my point x by x minus y. So this is equal to the integral of translate y of f. So this is just translate y of f convolved with g. Okay? Just I can move this guy to one of the functions that I want. Okay? So in this sense, what you want is that this at point x minus f convolved with g at the point x, this is just equal to translate y of g convolved with g at the point x minus f convolved with g at the point x. Now if I fix a g, if I fix a function g, the integral is a linear operator, so I can just write this as ty of f minus f convolved with g at the point x. Okay? Now I can just use Holder's inequality. Remember, if I wanted to use Holder's inequality here, this integral loses to what? Integral of f times g. Fix an x, so this integral loses to the LP norm of this guy, x minus whatever, right? LP norm, and then the LP prime norm of g. But this LP norm of f minus y, you just change the variables, just the LP norm of f. Okay? So this thing here loses to the LP norm of this times the LP prime norm of g. Now tell me why this goes to 0 when y goes to 0.
We prove this way.
Because we already proved that the translation is continuous in the primitive. So this goes to 0 as y goes to 0 because of the previous proposition. So this is why I'm assuming that p is less than infinity to use that. If p were infinity, then you do the same thing that we did for f, we would do for g. Okay, this goes to 0. Okay, so this takes care of one of the claims, right? That the f convolved with g is a continuous function. Okay, this I'm sure that it's continuous. That for every x, if I approximate change x plus y, subtract the value at x, this goes to 0 as y goes to 0. Now, why does it vanish at infinity? Okay, so this proves, okay, so this shows that f convolved with g is continuous. Good.
Because at some point g would be less than f, the integral would be less than epsilon, and for f would be the same, so I take this larger set, and it would be less than epsilon squared by Holder's inequality.
You have to be a bit careful with this argument, because f and g are not supposed to have compact support here, okay?
Yes,
But even if they are very small at infinity, I agree with you. If f is very small at infinity and g is very small at infinity, but you know the convolution.
This happens by integrabilities.
The convolution will always get some piece where g is large, right? So if I'm going to integrate this over Rd, so I am going to get a piece where g is large. This is g of y dy. So I'll be integrating over the piece where g is large.
I'm not saying f would be small, I'm saying the integral of f would be small.
The integral of f.
Of f to the p.
Of f to the p. Outside of a big ball.
Yes.
Yes.
Then we take the intersection of the two big balls and use all the inequality.
Yes, you can argue like that.
So, no, there is a about, I mean, for this, it means that it's not integral. It's,
Say that again. I will erase here, guys, okay? We already showed that it's continuous. Say that again, Carlos.
okay, well, if it's not going to zero at infinity,
Mm-hmm.
there must be some bound or some threshold for this, and somehow this integral must be infinite.
Well, no, you have to be careful. I mean, if it doesn't go to 0 at infinity, it doesn't mean that it stays bounded below.
Okay.
It might be going to 0 and doing this. And going to 0 and doing this. So it's not, the counterpart of this claim is not that it's going to stay bigger than 1/2. Going to infinity. It's just not going to 0, guys. Yeah. Okay, so we were in the middle of the proof. Let's see. We proved that f convolved with g is continuous. Check. Now I want to prove that it goes to 0 to infinity. Now it's the point where we want to show that f convolved with g belongs to the class of functions that are continuous and go to 0 at infinity, vanish at infinity. Do you agree that this claim would be very simple to prove if f and g had compact support? So if f and g have compact support, then the convolution has compact support too. Right? So if f and g have compact support, then so does f convolved with g. Right? I'm going to write here, but just to erase. But simply, if g has support in the ball of radius 10, and f has support in the ball of radius 10, then I cannot take, for every x which is bigger than 30, I'm out of business, right? Because 30 minus, this just exists when y is less than 10, and 30 minus 10 doesn't fall into the ball of radius 10. So, you see where I'm going. So if, no? Okay, so what I claim is that, so the point is that so this, let's make a claim here in the middle, which is that the support of the convolution f convolved with g is contained in the sum set support of f plus support of g bar. Okay, you take as a set the support of f as a set, the support of g as a set. You add these two sets.
You mean the union or?
No, I'm taking, so a plus b is just the set of points a plus b, where a belongs to a and b belongs to b. For a, b, two sets of Rn. I'm taking the sum set. And bar here is just the closure, right?
Why did you take the closure?
Well, it's not strictly necessary, but just to make it a compact set. Okay. Well, think about this claim. It's not hard to prove, because for this integral to exist, I mean, if you are at a point you have to be at this point x has to be written as x minus t and t where t is in the support of g, so this is not 0, and x minus t is in the support of f. Okay, so this point x, if it's not in this sum set, you'll never be able to integrate to write it as x minus t as t. So one of these two guys will always be 0 if it's not in the set. Okay, so this is why if you're out of this set, then this f convolved with g is 0 at that point. And then it's obvious that now if the support say is in the ball of radius 10 and the support is in the ball of radius 10, if you just sum the two sets, you fall in the ball of radius 20. And of course, if you're out of this ball, this convolution is 0. So this support is compact. Okay? So prove this. Once you believe in this claim, so if you have the convolution of two functions of compact support being compactly supported, I wanted to move towards the direction of what we wanted to prove before, like that the convolution of two functions vanishes at infinity. You have an LP and LP prime. By approximating by functions of compact support. Okay? So, coming back to the proof, what we want is that given epsilon bigger than 0, I wanted to show that there exists such n, such that this is small after n, right? So given epsilon bigger than 0, what I go ahead is that I go and choose functions in, say infinity of compact support, RD. I haven't showed you yet why infinity of compact support of RD is dense in LP, but it will follow from the discussion that we're going to have today, or perhaps in the next
Are we
class.
not going to prove this using convolution? So it's going to be kind of circular if we use it in this context.
Well, I am going to show using convolutions, but not this particular property of convolutions, that it vanishes at the infinity. I mean, it's not going to be necessary. Yeah, no, not going to use this. I'm not going to use this particular property that vanishes at infinity. But you have a good point. So I'll choose functions in infinity. Let's call it, let's say, f tilde and g tilde, such that let's see, they approximate. So let's consider the case where both of these guys are not infinity, right? Because I'm doing this approximation thing. So they're not infinity. So now I wanted to do the same sort of game. So I wanted to compare this point f convolved with g at the point x. I wanted to show that this is small. I'm going to add and subtract things. So let's see. I'm going to start with f convolved with x at g, and then I'm going to put this f tilde and g tilde into place. So it's going to be plus or minus f tilde g at x, and the plus f tilde g x, and then minus f tilde g tilde x plus f tilde okay, and then I break it into three integrals, remember, into three parts. So this is going to be just f minus f tilde convolved with g at the point x. The second one will be this 2. It's going to be f convolved with g minus g tilde at the point x. The third one is just going to be this guy at the point x. Now let's observe with me that the epsilon was given. I chose two functions f and g that are close to f tilde and g tilde that are close to f and g in this p norm or p prime norms. Let's say epsilon over 3. If I need more, if I need closer, I will come back and do it epsilon over 5 or more. But then this is what the object that I want to prove that it's small when x is bigger than a certain n. I add and subtract these guys that I want to put into play, these functions with compact support, and I break that in. They break the using triangle inequality. This last piece is 0
Outside of
if x is bigger than n. So this is equal to 0 if x is bigger than a certain n. That depends just on the support of f tilde and g tilde. Okay? This is actually 0, the property before. And why are these first two small?
Holder.
Because of holder, no? Right? So because of holder, these guys are less than f minus f tilde p, g p prime, and then here's f p, g minus g tilde p prime. So these are small because of holder, so I should actually choose f minus f tilde on p, epsilon divided by 3 times, let's say, the norm of g p prime if you want, then fp, yes, f minus g minus g prime, this is f tilde, right, and then here 3 or f3 if you want, but 2, so this is going to be small, this is going to be small, and this is going to be 0 if x is bigger than n. So this is going to be, everything is going to be less than epsilon if x is bigger.
But what about this f tilde? How do you compare the norm of f tilde to f?
There should be f tilde in
This guy here, right?
yeah, you see f tilde
Well, f tilde minus f norm LP was less than a certain number epsilon, right? So f tilde is certainly less than the norm of f plus f minus f tilde, if you want. Okay? So you can put f plus whatever you had before.
Sorry, what was the question?
Technically, he has a point. Here I have the norm of f tilde of p. But how do I compare the norm of f tilde of p with the f of p there? I'm saying that they're not far away. I mean, it's just, if this norm is less than epsilon, then the norm of f is less than, you can just put f plus 1. Let's say epsilon is less than 1 from the beginning. Okay, so maybe you put here epsilon plus 1. Is that okay? I'm just here writing f tilde as f tilde plus f minus f plus f, and then breaking. Okay, so this proves that this is less than epsilon for x bigger than n. Okay, so maybe we should take a look at the cases that we left out. So what happens if one of these two is infinity in the second claim? Is the result still true? So maybe I was too optimistic in the beginning. So the fact that this function is continuous, that's fine. But the fact that it vanishes at infinity, this proof here, since I approximated my functions by somebody that has compact support, I'm using that none of them is infinity. Now let's see. If we are in the case where one of them is infinity,
It is true.
and the other one is just L1, what do I get? I have to do the proof separately. Or maybe I didn't need in this proof. No, let's see.
If we write down the integral to the integral of f of x minus y times gy.
Yes.
Gy we can approximate it by the norm.
We can approximate it by the, we can bound it by the norm.
Bounded by the norm.
Yes.
Then you have f of x minus y. This. Yeah, yes. Then you can use again the same argument. I was suggesting that outside, for an integrable function, the integral would be, for an integrable function, the integral can be bounded outside a compact set.
This is not going to work, man.
Why not?
Because, say, for example, if G was identically 1,
Yes.
if G was identically 1, then F convolved with X, F convolved with G at the point X would just be the integral of F of X minus Y, G of Y, dy, right? So if G is identically 1, F convolved with G at any point is just the integral of F. It's just the, say, a norm of F. So if G was 1, then F was non-negative.
Yes.
So at any point, the convolution will be a constant function equal to the integral of F.
Can't go to.
It can go to 0, it will just be a constant function. Okay, so it doesn't go to 0 at infinity. So, blah, 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 then this is a continuous function, that vanishes at infinity. So for the second part here, I need 1 less than p less than infinity. Okay? It is always a continuous function for p up to infinity, but it only vanishes to infinity.
My argument assumed that g of y is going to be 0 outside something, but it's not the case.
Well, I mean, but you cannot guarantee that an infinity function has this property.
Yes, yes, of course.
So I'm taking the simplest infinity function that you may guess, constant equal to 1. Okay? And then this is a counterexample to the claim that it vanishes at infinity, the convolution. So this is the right statement that we wanted to discuss. So if you get functions f and g in LP and LP prime, then the convolution is continuous. And if none of these exponents are infinity, it actually vanishes at infinity. Good. Okay, this is another example of a resultant analysis where we used the convergence theorems and we used the approximations by a dense class of functions. Although I haven't technically shown to you why IC infinity of compact support is dense, but we never actually used the fact that this class here is we never used that it was infinity. We just used the property that it had compact support. So you could actually have approximated your functions by functions which are step functions, which have compact support, or which are simple functions which have compact support. Well, simple functions do not necessarily have compact support. The sets have finite measure, but they be sets that go to infinity. So let's just, if you don't like this now, you replace by step functions, and we are okay, and we have proved. Okay? Okay, I want to leave you guys with one exercise to go home, and then we break it for today, which is the property. I want you to think about this Young's inequality. So, as an exercise for today, prove this so-called Young's inequality. Let's say let 1 less than or equal than P, Q, R less than or equal than infinity with 1 plus 1 over R equals to 1 over P plus 1 over Q. Then, if F belongs to LP of RD and G belongs to LQ of RD, this implies that F involved with G belongs to LR of RD and the LR norm of convolution loses to LP norm of F Q norm of G. Okay? This is what is known as Young's inequality. And this is the the decay properties that I was telling you in the beginning that guarantee the existence of the convolution. So in the beginning, when I defined convolution, I should have been a little bit more careful and say, just take f and g positive functions. So if you take f and g positive functions, the integral that defines the convolution is well defined. It may be infinity at some points or at all points, but it's a defined thing. Okay? Now, if you have that f belongs to LP and g belongs to LQ, then this convolution will belong to LR because this bound holds. Automatically then, this function will be finite almost everywhere. It cannot be infinite almost everywhere. It cannot be infinite on a set of positive measures because otherwise this norm would be infinite. So automatically, if f belongs to LP and g belongs to LQ, the convolution is finite almost everywhere, and it belongs to LR, where R is given by this combination of exponents. So what we did before was essentially a particular case of this. If you are with P and P prime, this side adds up to 1, so your R in this case is infinity, and what I'm saying is that the L infinity norm of the convolution loses to the LP norm of f times the LP prime norm of g. A fact that you already knew by Holder's inequality. That's Holder's inequality that we used several times here in this proof. Okay? So this is a more general statement. Take this home and think about it. We start next class proving Young's inequality for convolutions. Okay? Good, guys. Let's break it for today. And we continue on Friday at 4.